continue, well, really start discussion of periodic trends, because we didn't get very far into the trend side of things yesterday, which is fine. Reminders, your one-pagers for 1.3 are due tomorrow. If you cannot get them to me tomorrow, but you can get them to me digitally on Thursday, that is also okay. But I would like to have time to look at them and get it back to you before the quiz on Monday. So let's try to get those into me when you can. Quiz corrections due on Friday. Let's see. Oh, let me give back these before I forget and they disappear into a pile. So there are some, we talked yesterday about the, why we call them S, P, D, and F in terms of the blocks on the periodic table. And this is a couple of images. This is from an old paper, and this is from a blog post that I linked in Canvas, showing the spectral lines from sodium, two different versions of this. And they've been, you can kind of see the whole thing smeared together, and that's what it would look like if you look in the Elements coffee table book for, let's see, where is sodium? You can see some of the emission spectrum here, but it doesn't look quite like that. So that's more complicated than what we are able to see through our spectroscopes. But the point is that they were able, they had, people were pouring through these images and saying, what do we call these things? And so that's where they started assigning terms. And there were lots of different terms, and it was Hund of Hund's rule who kind of popularized these four terms in particular. But he was not the one to start using them. For sharp, S for sharp, and the s orbitals are the most compact spherical orbitals, and so the transitions to those orbitals, I think it's to the orbitals, are going to have the crispest lines. They put principal for P, diffuse for D, and fundamental for F. They were kind of wrong about principal and fundamental, but that's where those letters came from, and we still use them. So, all right, so the trends. Almost all of the trends that we're going to talk about, and all of the trends that we talked about in honors chemistry, are driven by the forces of attraction between the nucleus and the electrons. Okay, and when we have things with opposite charges attracting each other, or like charges repelling each other, there's kind of the Coulomb's law can give us a sense of how we can calculate that force of attraction. You are not going to be required to do these calculations. This equation is not in your data booklet, okay? But I want you to understand where this is all coming from. You did actually, in honors chemistry, do a whole packet on Coulomb's law right at the beginning of periodic trends. But it didn't specify the equation quite so much. But the idea is that we've got these particles, whether they're being repelled or being attracted. The force of attraction or repulsion is going to be directly proportional to the charges, the relative charges of the particles, and then divided by the distance between them squared. Okay, so what this tells you is that the charge matters. The charge is essentially squared if we take it across the two particles, and the distance is squared. So both of those things play a role in how strong the force of attraction is. When we're talking about, say, valence electrons, our charge on the valence electron is just -1, okay? And the charge on the nucleus is how many protons we have, okay? So that's the number of protons in the nucleus is going to have an effect on this force of attraction. It's going to more protons, more attraction, okay? The distance, though, the more protons we get, the more electrons we get, and the more energy levels we get. So the distance is also important. The further away we get, the weaker. So regardless of the fact that we have more charge, we actually still have weaker attraction when we're farther away from the nucleus. Okay? That's what we teach you in Honors Chem. IB brings into it another layer of things that affect this force of attraction, which is electron shielding. Okay, so we're going to skip the blocks on the next page because we've already pretty much talked about it, and skip right to page 5. So when we talk about electrons outside of just the original build an atom level discussion, we mostly focus on the valence electrons. Once we're past electron configuration, we're really focused on the valence electrons because those are the ones that are doing everything, right? It's like those are the ones that are on the sweatshirt that you're wearing. Doesn't matter if you have a cool t-shirt on underneath, it's the logo on your sweatshirt that everybody can see and that, you know, is your identity in that sense. But those core electrons do actually play a role because they're kind of, you can think of them sort of like layers of insulation between the valence electrons and the nucleus. And because the electrons all repel each other, having a bunch of electrons between you, the valence electron, and the positive charges in the nucleus actually kind of buffers attraction a little bit. Okay? So it makes it a little bit weaker. You've got all this like charge repulsion happening in here before you get to the positive charges attracting you. So this plays into some of the reasoning behind the trends that you're going to be expected to understand. Okay. So shielding as we go across from left to right within a period is going to stay the same because we have the same number of core electrons. We're just changing the valence electrons. Okay, so we're keeping the shielding the same, but we're increasing our protons. Okay, so that is why we are getting a stronger force of attraction between the protons and the outer electrons as we go from left to right. Yes?
How can that be the case across the whole period? Are we just not getting into like low enough for the transition?
So, yes, I guess there probably is an effect of having the d orbitals full or not full, but I'm not sure it is big enough to take into account at the level that we're looking at. I think having a whole another occupied energy level is going to be a bigger deal than having the previous energy level filling in some d or f orbitals. At this level, that is all you need to. But this is the level that you're going to be required to know. I'm sure that has some effect on some level. I don't know how to calculate that though. So I'm sure you're right. But if anything, so you might see a difference between blocks. You know, the S block versus the P block, for example, in the same period, because one of them doesn't have d electrons in the previous energy levels, one of them does. Yeah, there's probably some effect there. But I think, based on the data that we see, we're still going to see an increased force of attraction as we go across, regardless of whether we're looking at like period 3 or period 6. And we can actually look at that on the best website on the internet if we want to. In fact, let's just do that because we're talking about it. Now I have it up. So let's use ionization energy real quick. So ionization energy is increasing as we go across, or actually let's not use ionization energy because we're going to talk about discontinuities later, and I don't want to talk about it right now. Let's look at atomic radius. So you can see that atomic radius is decreasing as we go across in every period, okay? If we graphed this and we looked at the change between S block and P block as we went down by period, I'm not sure that we would see a difference like in the slope. Doesn't look like it. So that would suggest that the D electrons don't actually make a big difference in terms of the amount of shielding. Yeah, it's a great question, and I don't really know the answer. But it looks like it doesn't have enough of an effect for us to worry about it. So we'll leave it at that for now. As we go down a group, though, the shielding increases because we're adding energy levels. And so not only, so as we're going across a row, not only are we adding charge and therefore increasing the Coulombic force, but we're keeping shielding the same, okay? With the possible exception of the D and F, which, yeah, that's a very interesting question. As we go down, we are adding more shielding. We're adding another layer of insulation, and we're getting farther away because we've got those electrons underneath. And all of the electrons are repelling each other, which is what pushes the outer energy levels further away. They don't want to sit in the same space. So if we kind of wrap that in to thinking about the Coulombic forces, we can start thinking about it in terms of what's called effective nuclear charge. And this is going to be a very simplistic way of thinking about this, but it's still useful. So we'll go with this. This is what you're expected to be familiar with. So nuclear charge is really just how many protons do you have. But we can talk about, from the perspective of the valence electron, the effective nuclear charge is essentially the net charge that the valence electrons are experiencing if you take into account that all the core electrons are in the way, okay? And so basically we just subtract. It's really straightforward, okay? We take the atomic number, the number of protons in the nucleus, and we subtract the number of shielding electrons, which is going to be our core, not valence electrons. So you're going to only count the electrons that are not in the valence shell as shielding electrons. And you're going to end up with a number, okay? I mean, I guess, I'm sorry, going back to, this is percolating in my head, going back to your question. Because as you're filling those D and F orbitals, you are also adding more protons. So I think that it kind of washes out if it's in a previous energy level that already exists. Sorry. Anyway, so if we look, say, at this potassium atom that we were just looking at, our effective nuclear charge, equal to the nuclear charge, which is also the atomic number, right? Minus shielding electrons. Our atomic number here is 19. Everything except the valence electron, the one valence electron, is a shielding electron. So this would be equal to 1. That's it. It's that straightforward, okay? The idea being that it sort of mitigates the effect of having the more protons because of also the increase in shielding as we go down a group. Okay. All right, so how does this play out? We've already talked about some of these trends, but let's talk about them in the sense of why. Because you will notice it says atomic and ionic radii values can be found in section 10 of the data booklet. Well, data booklet section 6 gives you the names of all the elements since they're not actually on your periodic table, but you have them here. So you don't have to memorize them, and it's not even like it was back in the old days of 2 years ago when you didn't have this for paper 1 for the multiple choice. Now you do. So section 7 is just your bog standard periodic table with the atomic numbers, symbols, and average atomic mass, relative atomic mass. Okay. Section 8 is also a periodic table, but this one has melting points and boiling points of the elements. Section 9, also a periodic table. First ionization energy, electron affinity, and electronegativity. Section 10, also a periodic table. This one has the atomic and ionic radii. Okay? So, the warm-up that I had you do yesterday, that's the end, by the way, of the periodic tables. The warm-up that I had you do yesterday, like, do you remember what happens? You don't need to memorize that because the data are right here. If they ask you something about how does the atomic radius change, you just look at atomic radius and you say, it is getting smaller. So that means that they're not going to ask you that question, right? So they're going to ask you why. And so making sure that you understand why is the key to this topic. Okay. So atomic radius decreases across a period, and that is because our nuclear charge increases, our electrons are being added to the same main energy level, so shielding stays the same, and so essentially our ZF goes up as we go across, right? Our effective nuclear charge increases as we go across, and that plays into our force of attraction. So since we define the radius as sort of, there's a lot of ways to define a radius, the radius of an atom. When we talk about just a sphere in math and geometry, radius is just the distance from the center to the outside. But our atoms, even though we like to draw them like this with a nice, or, with the Bohr model orbitals, we know that that's not what they really look like. They're clouds of probability. How do you know where the outside of the atom is? How do you define that? So you'll notice that there's this definition measured as half the distance between neighboring nuclei. Okay? So if we have a sample of that element, that's essentially what we're looking at. Now, obviously, different elements do different things, whether they're metals or nonmetals or whatever. So there's going to be some squidginess in there. Okay? This is the definition that you should be aware of. And the reason for that is that we can actually pinpoint where are the nuclei and how far apart are they if we have the right specialized equipment. We cannot say at any moment in time where the outside electron is. So measuring between the two nuclei and calling half the distance the radius is the easiest way to do that. If we go back to the best website on the internet and we go to radius, you'll note that on here there are several options. Calculated, empirical, covalent, van der Waals. These are different techniques for measuring those distances. And so you will see, no matter which one of these you pick, this trend is the same. The exact numbers are going to be a little bit different, okay? So we're not really worried about that. We're just going to call it the distance between the two nuclei and, call it a day. Okay, so radius decreases as we go across because our effective nuclear charge is going up. Shielding stays constant, number of protons goes up. Down a group, we are increasing the number of protons, but we are also increasing the amount of shielding. Number of occupied energy levels increases, so shielding increases. Which means that our effective nuclear charge is going to be lower as we go down the group. Okay. And so the electrons, as we go across, those outer electrons are going to be pulled in closer because of that stronger force of attraction. Okay. As we go down a group, they're not going to be pulled quite as hard because they're further away. Okay. Also because there's, they're further away because there's that repulsion between like charges. Okay. Okay, so that's atomic radius, and we've covered that in Honors Chem. This should feel pretty comfortable at this point. Twist that we're adding in this class is, one of the twists is ionic radius. And if you think about how a lot of elements are found, we don't usually find sodium just out by itself, right? It's most reactive, it's in the most reactive group of metals. You're not going to find it in nature as pure sodium. You're going to find it in an ionic compound, which means it's not going to be a neutral atom of sodium. So thinking about the radii is important to think about in terms of the ions, just as much as it is the neutral atoms. So I'm skipping and then skipping page 7 and then going back to it. If you want to have both open, that's fine. But the key thing to realize is that we're talking about, you're only going to be responsible for ionic radii of the main group elements where we know what kind of ion they're going to form, okay? Not transition metals, not the post-transition metals, not the lanthanides and actinides. So the ions that we're talking about, so this is not like ionization energy where we can have first, second, third, fourth within an atom. It's this element is going to make a +1 ion or a -2 ion, like always. And that's the radius that we're looking at, okay? So positive ions, we're losing the valence electrons, right? So they're going to get smaller because we're losing a whole energy level. By even when it's just one electron getting plucked off, that makes the radius smaller, okay? So because they have fewer occupied energy levels, and then also we've lost an electron, or multiple electrons, but we haven't lost any protons, right? So the proton-electron balance is going to be a little bit stronger in favor of the protons as well. You're not going to have, but you're going to have less shielding in your new valence electrons because you've lost the old valence electrons, okay? Negative ions are going to be bigger than their neutral atom. And you might think, but they're not adding an energy level, we're just adding electrons to the same energy level. So our chlorine atom is we're just dropping one more electron in that third energy level. But because of the repulsion of the electrons against each other, they're going to be shimmying around to make space for that other electron and pushing each other a little bit further apart. So that shows up when we measure it as an increase in the size of the ion. Okay. So extra repulsion, and yeah, the electron-proton balance is the other way. So when we then look at it as a trend going across the table, which is now we're back on page 7, we kind of have two things going on. Okay, we have the decrease that we see when we go across the table in the atomic radius. We also have that in the ionic radius. Okay, so here and here, we're seeing the decrease just like the atomic radius because of increasing effective nuclear charge. But the jump, but different than the jump that we see in successive ionization energies, is because we are adding another energy level when we flip from being a positive ion to a negative ion. Okay. So in this case, in period 3, the cations have only 2 occupied energy levels, the anions have 3. But within the cations and within the anions, we're still seeing that overall trend. I kind of wish they put atomic radius on top of this. I'm going to write that down because I actually want to plot that. Lot, atomic, and ionic, period 3. Okay. So this diagram is not in your study guide, but I've used this for a number of years. It's one of my favorite visualizations out there. What this is it's showing you atomic and ionic radius at the same time in terms of the hemispheres. So each element has a left and a right hemisphere. I maybe would have done it a little bit, I would have flipped these, but I understand why they did it this way. The gray is the atomic radius in all cases, and the black numbers are the atomic radius. So the gray hemisphere, you can see, is getting smaller and smaller and smaller and smaller as we go across. The pink is for the cations that have lost an energy level, so you can see that it drops down from the atomic radius, but then still continues to get smaller. And the blue is the anions. And it's a little harder to see. It doesn't change quite as much, but it is going down within the anions as well. Okay, so just another way to visualize it. But I do want to make that chart. I do want to make it as a graph. Okay. Oh, so I think we talked about this in electron configurations, the concept of being isoelectronic, meaning you have the same electron configuration as another atom, even though it's a different element. Maybe we did not, but that's a term you should know, is isoelectronic. I mean, iso means same, and it just means you have the same electron configuration. So all of these ions have this exact same electron configuration, okay? And they are all isoelectronic with a neutral neon atom, okay? But you can see the same thing is happening here. I mean, this is just showing this in table form, and also making these guys in period 2 and these guys from period 3 that have the same numbers of electrons when they form ions. They're all isoelectronic with neon. So again, you can see that our ionic radius for the cations is going down, and as it's continuing to go down as we go across. And same thing here. The ionic radius is going to be bigger for the anions, even though these are in a whole period above, before. Their ionic radius is bigger than the ionic radii of the cations in the next energy level. And you can see this at any junction around a noble gas. Okay, so go ahead and on page 9, do question 3 and 4. Okay, answer questions 3 and 4. I'm gonna have you skip 1 and 2, and I mean, you can answer 5 if you want, but we're just gonna talk about 3 and 4. And we are actually making good time, so I need to add a little bit. Yeah. So they're what? Okay. If you think about a lithium atom, we're going to have our nucleus, our protons here, and we're going to have 2 electrons in energy level 1, and we're going to have 1 electron in energy level 2, right? The ion is going to remove that. So then we're just going to have energy level 1. Okay. So it's true that there's going to be less repulsion with just 2 electrons versus 3, but we're also now constrained just to that 1s orbital. Okay, so the ion is going to be smaller. Okay, I think maybe you meant that and then you just said it backwards. Fluorine atom or fluoride ion? Jocelyn?
The fluoride ion is bigger.
Mm-hmm.
Because
So this is going to be, we're losing an energy level, essentially. And this is going to be more repulsion. Okay. I've realized just during lunch, I had accidentally posted the reactivity 3.1 and 3 in the answer key yesterday. So I went back, I took those out, I put the structure 3.1, which is what we are actually doing right now. So the answer key is there if you want to go and check your answers to any other questions. I want to try to get through a few more things here. Back to ionization energy. Now we're not talking about taking multiple electrons away from a single atom. We are focusing on first ionization energy, okay, of different elements. And they used to love putting graph questions like this on the test. I haven't seen as many graph questions in more recent years from the question bank, but they could always throw something at you and not give you the y-axis labels and say, what is this trend in? Okay? So being able to think about what would this look like as we're going from atomic number 1 to however many are on the graph, what would that look like is important, okay? So they point out below this that there's basically two trends happening when we look at a graph like this. So one of the trends is that as we go across a period, we increase the ionization energy, right? And that happens here, and it happens here, and it happens here, okay? And then the other trend is that as we go down a group, we're decreasing, right? And we can see that happening, with each group. Here we are even down to the, it's a little bit harder to see. It's slight, the slope isn't quite as big in group 1, but at least in this graph. So that's kind of the main take-home message for the ionization energy. And you'll see that we've got that definition that I've been harping on for ionization energy here. Energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. So you can think about it in terms of 1 atom losing an electron, but when we talk about the actual kilojoules per mole, the numbers that you'll find on P-table and the numbers that you'll find on your periodic table in section 9, that's going to be per mole. So we're thinking about it in terms of moles. But it's the same, the trends are going to be exactly the same. It's just that the absolute numbers here would be different. Okay, so being able to recognize that and why, being able to explain why, is important, okay? I will pull one of those questions out for you guys for tomorrow. Graph question. So you can see what I mean about that. So we've got increased number of occupied energy levels. That gives us more shielding. It increases the distance to the nucleus, lowers the Coulombic force of attraction as we go down a group. As we go across, we're increasing because we are seeing an increase in effective nuclear charge because of the increase in protons, although our electrons are being added to the same energy level. I don't think I need to say anything else here. The discontinuities we're gonna talk about in the next packet. Okay, and those will make sense to you after what we did in the last topic, which is one reason why he puts them in the last topic, but I like them better here. Electronegativity, the other one that we've talked about in honors chemistry. Also, I would make flashcards with the definitions, or put them somewhere. Have a definitions spreadsheet or something. So it's ability of an atom to attract bonding electrons. Okay, so that's very important. We're not just talking about general attraction of electrons. We're talking specifically about within a bond. Okay. Typically, we are measuring this on the Pauling scale. It goes up to 4. You can find this in your data booklet. And the reasons for the trends in electronegativity are exactly the same as the reasons for the trends in ionization energy. Okay, it's stronger Coulombic forces going across, weaker Coulombic forces going down. Okay. If we look at, this is something we talk about in Honors Chem, but just as a reminder, if we look at a bunch of these things, we can look at ionization energy, we can look at radius. If we look at electronegativity, you might notice that some, aside from our more recently found and unstable elements, we've got 3 elements that notably lack an electronegativity: helium, neon, and argon. So why do we not have numbers there at all? Ella?
Because they don't bond with stuff.
They don't bond. Okay, we can make them bond under really, really severe conditions in a laboratory, in a very high-tech laboratory, but pretty much you will never see them reacting with or bonding with anybody. So they can't have an attraction, an affinity for bonding, or we can't measure what that would be because it doesn't happen. So you could say, well, maybe it's 0, but we do have a number of molecules that form with krypton and xenon, and we can measure electronegativity in those. But if there's no bonding, we can't measure it at all. So we just leave it blank. Okay. So a lot of times people think about electronegativity as like the opposite of ionization energy, as attraction for electrons instead of, removing electrons. But really, what that is another property similar to, slightly different from electronegativity and ionization energy, and that is called electron affinity. This is more properly the sort of opposite of ionization energy, in that we're still talking about gaseous atoms. We've got a mole of gaseous atoms, and instead of removing 1 electron from each of them, we are now adding 1 electron to each of them. Okay? And when we do that, we release energy, because having those electrons just floating around not attracted to anything is actually a less stable state than having them be attracted to a nucleus, even if it's an element that would normally form a cation. Okay, so there's still energy released when we add electrons. It's really energy from the electron's point of view, more so than from the atom's point of view. We'll continue this tomorrow. All right, thanks, guys.